Hello everyone, and thanks for taking the time to attend this talk. I'm Mahmoud Khaled, and I will be presenting today the tool paper, OmegaThreads Symbolic Controller Design for Omega Regular Objectives. This is a joint work with Majid Zamani from University of Colorado Boulder. We start with a motivation. Cyber-physical systems are collections of computational devices that interact with or control physical systems. Examples of cyber-physical systems are airplanes, smart grids, and surgical robots. Safety-critical cyber-physical system is a subclass of cyber-physical system where failure or malfunction may result in death or injury to people, loss or damage to equipment or property, or environmental harm. Safety-critical control software is the brain of safety-critical cyber-physical system. It interacts with sensors, performs control and planning tasks, and finally commands the actuators. An example of life-critical safety-critical control software is the software in insulin pumps. Ensuring the correctness of safety-critical control software is then very crucial. To ensure the correctness of safety-critical control software, we should investigate why things go wrong with safety-critical control software. The question is then, why do things go wrong with safety-critical control software? Simply, the design cycles of safety-critical control software permit mistakes. Here is a diagram of the development cycle of safety-critical control software. Such waterfall software model, although not exactly what is used today in today's industry, it has the parts that we need to pay attention to. It starts with requirements collection, where the design requirements of the software are collected and analyzed. As humans are responsible for collecting and documenting the requirements, we may get requirements that are false, ambiguous, and also may be miscommunicated to people responsible for next tasks. Next step is design and development, where the actual software is designed and coded. As software developers are humans that do mistakes, we may expect bugs in the codes. Some of these bugs are logical ones that are hard to find. Some requirements may also be ignored. Next is testing. The problem with testing is that we can't cover all testing scenarios, and consequently, many edge cases are left undetected. Testing is also exhausting and repetitive. Finally, deployment. Here, problems happen when integration and deployment is not well planned. You may expect faulty representations of the design software, hardware incompatibilities, and final product instability. Generally, we need to find new ways for specifying the requirements in more precise, formal, and unambiguous way, so that we can safely communicate them. We need to automate the design and development tasks, giving no chance to human-related bugs. We need less testing effort through development steps that produce software we can trust. Actually, we need to have certifiable safety-critical control software design approaches. There is a promising group of approaches called formal methods in control. They provide automated synthesis of certifiable software. The software is guaranteed to satisfy the requirements, and post-development testing may not be needed. They can also handle complex, high-level specifications. An example of formal methods in control is symbolic control, and we discuss it next. Symbolic control is an approach for automated synthesis of controllers for control systems. We start with a dynamical system described by some mathematical model. As the state of the model have infinite values, we cannot work with them algorithmically. Instead, an abstraction is constructed from the model. This comes in form of a finite state system that we refer to as the symbolic model. A formal relation between the original system and the symbolic model ensure that the controller synthesized for the symbolic model can be refined to work with the original system. The synthesized controller is referred to as the symbolic controller. Once refined, it ensures that the given specifications are enforced on the original system. We will discuss symbolic control formally later. The main question here is then, is it practical to use symbolic control for today's safety critical control software? Unfortunately, the answer is no. Symbolic control suffers exponential complexity in constructing the symbolic models and synthesizing the controllers, a problem that is known as the curse of dimensionality. Due to this problem, the design and development phases of safety critical control software may take long time and may not finish. This also limits symbolic control to small-sized systems with less curse of dimensionality symptoms. Although symbolic control permits specifications that are formal, all tools of symbolic control is still considered naive and impractical specifications. The deployment of symbolic controllers is based on ad hoc techniques that ruin the formality and guarantees obtained from the symbolic control approach. During the last few years, we have been investigating new ways to make symbolic control more practical, and we are pursuing three main directions. First, using scalable parallel algorithms for abstraction and synthesis allow us to mitigate the effects of the curse of dimensionality. 2 years ago, in HSCC 2019, we introduced p-phases as a framework for designing and implementing such algorithms. We showed that using variable computing resources and scalable parallel algorithms allow controlling the time complexity of the algorithms of symbolic control. In this talk, we will pursue two more directions. We will introduce a tool to extend the support of specifications and unify the synthesis process. We will also provide a standard formal approach to controller extraction and code generation. Let me first introduce p-phases briefly. p-phases supports all computing platforms, CPUs, GPUs, hardware accelerators, and their interconnections. p-phases is kernel-based framework. This means that developers implement their own logic as kernels that run on top of p-phases. This modular design allows for maximal extensibility. For symbolic control, p-phases was used to design parallel algorithms for constructing the symbolic models and for the controller synthesis. There are currently open source tools for formal methods in control that are based on p-phases, like for example, Amethyst for the synthesis of controllers for stochastic systems, PERC for the parallel reachability analysis, and OmegaThreads, the one we are introducing today. If you are working within a similar research direction, or simply need to accelerate your algorithms, I suggest you give p-phases a try. It's free to use with a demo version. We have multiple example kernels that use p-phases, which can be used as a guide. Next, we go back to symbolic control and how we can improve it as planned. We need some preliminaries. We start with control systems. A control system sigma is a tuple x, u, f, where x is a set of states, u is an input set, f is a continuous map satisfying a general Lipschitz assumption. A trajectory of sigma is defined by the locally absolutely continuous curve z if there exists a continuous curve nu that satisfies this ODE. On the other hand, a system is a tuple x, x0, u, t, where x is a set of states, possibly finite, x0 is an initial set of states, u is an input set that is also possibly finite, t is a transition relation. We say that x is symbolic if x and u are both finite sets. For an x, we use ux for referring to the inputs admissible to x. A sample version of sigma called S tau is a system x tau, u tau, and t tau, which encapsulates the behavior of sigma at sampling times k tau. You may think of it as a control system surrounded by a sampler and a zero order hold. We use this simplified version of systems with 3 sets when the initial set equals the state set. In S-tau, a transition of S-tau is a tuple, a starting state, a piecewise curve of input applied to sigma, and the final state reached after tau seconds. The symbolic model is then a system SQ, where XQ is a finite cover or partition of X tau, and UQ is a finite subset of U tau. TQ is designed such that there exists a feedback refinement relation from S tau to SQ. Interested audience can find more details about feedback refinement relations and the construction of the symbolic model in the paper below. Let's now introduce the specifications. Considered sample time system S tau. Let Px and Pu be sets of atomic propositions, labeling subsets in X tau and U tau respectively, such that Px intersect Pu is empty. A specification for S tau is a subset of all omega words of P, where P is the power set of the union between Px and Pu. The figure at the right shows an example of Px. Px comes with a labeling map that takes the states of X tau to subsets of Px. Similar example can be made for Pu and a labeling map of it. Now, given an initial set of states x0, a sequence of inputs u tilde, and a resulting sequence of states x tilde, S tau is set to satisfy the specification psi if, for any initial state, there exists an omega word alpha in psi such that for all time instances, the union between the mapped states and mapped inputs should be in the current subset in the word alpha. The figure at the right bottom visualizes such condition. Asking the user to provide their requirements in omega words is not practical. Instead, LTL or deterministic parity automata are used. DPAs are more expressive, and any LTL can be represented with some DPA. A DPA is a tuple, Q, Q0, gamma, TA, X, D, and P, where Q is a set of states. Q0 is an initial state, gamma is an alphabet, TA is a transition map, X is the transition coloring map, D is the maximal color, and P is the parity defining which runs of A are accepted. A run mu is accepting if and only if the highest value that occurs infinitely often in the sequence of color transitions is even or odd, depending on P. Given a system S tau and DPAA such that gamma is equal to P and psi is the language of A controller synthesis problem is asking to find a controller C such that S tau satisfies psi when the applied input sequence U tilde is coming from the controller. Now, starting with sigma and its sampled version S tau, we construct a symbolic model SQ as usual. On the other side, specification of psi is represented with a DPAA. Having two finite state systems SQ and A, we can combine them in a special way to construct a parity game P. Solving the parity game will give us a controller that enforces psi on sigma. A parity game here is a two-player game played between SQ and C. It's represented by the tuple VS, VC, V0, ES, EC, and K, where V is the set of nodes the symbolic model plays from, VC is the set of nodes the controller plays from, V0 is an initial node of the game, ES are the edges played by the symbolic model, and EC are the edges played by the symbolic controller. And K is the coloring map of the edges in EC. We introduced an algorithm for constructing P from the symbolic model and A. It simply constructs P by exploring the symbolic model and the DPAA simultaneously and constructs a product-like object representing the parity game. The algorithm is discussed with more details in the tool paper. Having a parity game P, one can use an off-the-shelf parity game solver like the one in Tool-Strix. It can be also parallelized and unadjusted to work with P phases. The solver simply marks one or more edges of EC for each edge of the symbolic model as winning counterplay edges. The strategy is then extracted as a winning set of play rounds called tilde W. For a round in tilde W, C wins by applying an input U that labels the edge EC. When the symbolic model, it chooses state X that labels the edge ES. Those edges are marked, for example, in green in the right figure. The strategy can be non-deterministic and it is extracted as a Mealy machine C. All details about the definition of C are provided in the tool paper. OmegaThreads is designed as a kernel built on top of prefaces. User's input is provided as simple text files. A text configuration file describes the problem. This includes the quantization parameters for constructing the symbolic model, the control inputs, and the atomic propositions. Requirements are given as text LTL formula in the configuration file or as separate DPA files. The system dynamics are given in a separate file. OmegaThreads then constructs the symbolic model in parallel. The specification is translated as DPAs in the case they are provided as LTL formula. A parity game constructor takes the symbolic model and the DPA as input and constructs the parity game. A parallel parity game solver solves the game and generates a dynamic symbolic controller as a Mealy machine. A code generator can either produce a raw version of the controller or can generate code from the controller. A Python interface and a 2D simulator are provided and can be used by the user to inspect and test the raw controller. The automatically generated code can be finally used for the deployment. OmegaThreads supports the 3 major operating systems, and a Docker version of OmegaThreads is also provided. Finally, it's open source and available on GitHub. Let me now show you with an example what OmegaThreads can do. Consider the following drone model. The drone operates on a battery and it is described by a nonlinear impulsive system. Variable x1 and x2 are used to represent the lateral dynamics of the drone. The impulsive part represents the discrete time effect of the battery charging and discharging. The battery level is encoded in state variable x3. The control objective is provided as LTL formula shown on the right side. In a simple language, this asks that the drone performs infinitely often 2 different pickup and delivery tasks, pickup 1 and 2, and delivery 1 and 2. When a delivery task starts, it should be completed without starting another delivery task. Some obstacles must be always avoided, and the battery must not reach a low state. Finally, from time to time, it should be fully charged. The problem is provided to OmegaThreads as text file, and OmegaThreads solved the problem in around 2 seconds within a MacBook Pro machine. Now let's summarize. Current symbolic control tools accept impractical and limited specification. Using ad hoc techniques for deploying the symbolic controllers negatively affect their correctness. We introduced OmegaThreads to support Omega regular and LTL specifications. It constructs symbolic models from control systems, DPAs from the specifications, and parity games from the product of symbolic models and the DPAs. OmegaThreads solves the parity game, extracts the symbolic controllers as Mealy machines, and automatically generates their software codes. Future works will focus on implementing a data parallel version of the parity game construction algorithm, generating counter strategies to identify any error in the model or the specification, and finally, allowing the users to specify objective functions used during the synthesis to find user-defined optimal strategies. I'd like to acknowledge ERC for supporting this work through the ERC Starting Grant Auto CPS. I conclude my talk by providing a demo showing how simple and easy it is to use OmegaThreads to design automatically controllers for control systems. So OmegaThreads is available open source in GitHub, and I will be using the Docker version. Let me make a folder for this simple tutorial. Now I pull the Docker image. Now I run the Docker container. Now we are inside the Docker container of OmegaThreads. I navigate to OmegaThreads. Let's update it. And rebuild it. Now we run the pickup delivery drone example. Now OmegaThreads has finished computing the controller. Let's extract the controller from the Docker container and run the simulation. Now that I extracted the controller files from the Docker container, I'll run the simulation locally.